In today's video, I want to discuss how we can test a trading strategy and optimize its parameters. This is a vital step in quant research and often underappreciated. We will build some code with which we can automate the process. I've chosen a simple moving average crossover strategy as an example, and you will see that there is more in it than initially meets the eye. During this process, you will learn some facts that may surprise you. Be aware that the MA crossover is not the world's most profitable strategy and merely an example, but with some small changes you can apply this methodology to your own strategies on a large scale. If you enjoyed this video, please don't forget to subscribe and hit the like button. It will help us to produce more content like this for you. So today, we will discuss the following. Download free market data. Build a fast and efficient backtest. Determine what type of parameters should be used. Then we use system parameter permutation, how to test for overfitting, visualize the results in different ways, and do a grid search for further optimization. So let's get started. First we define some stocks. Here we choose some large cap US equities for simplicity. Next, we use the Python package yfinance to download market data. We need to define the period we want to look at, in this case 20 years, as well as the granularity, which is chosen by 1 day. When we choose auto-adjust equals false, we end up with an adjusted close column in our data, which is most convenient for us. This code returns a data frame with multi-index columns. We need to make sure that this is handled correctly. Now that we have the data, we are ready for building a strategy. The moving average crossover is probably one of the oldest systematic trading strategies. I've chosen this particular one for its simplicity rather than effectiveness, because this workshop mainly focuses on strategy optimization rather than finding a good system. The system enters a trade when one moving average crosses the other and flips the trade on the next cross, and so forth. This way we get a continuous sequence of long and short trades. Implementation is fairly straightforward and can be done in only a few lines. First, we get the data and use TA-Lib to create two moving averages with different lookback windows. We want to make sure to always assign the shorter lookback to the first moving average and the longer lookback to the second moving average. Next, we calculate the difference between the two. Now we can build a trading logic. We loop through all the available data starting after 2 years to avoid the initial NANs or invalid data points. A trade is entered when the sign of the current moving average difference is different from the sign of the previous moving average difference. Depending on which way our MAs cross, we trade from the long or the short side, and the polarity variable gives us the flexibility to run the system from the opposite side. At each time step, we record the unrealized P&L as the percentage difference between the current and previous price times the trading direction. This needs to be done before we switch the trade polarity, or otherwise our results will be wrong. That's all we need to define the strategy, but be careful. Small mistakes in signs and sequences can produce completely wrong results. So please check your trades and results carefully when you design a new strategy. Let's run an example strategy for Oracle with an arbitrary lookback window of 20 and 60. To plot a P&L curve, we need to calculate the cumulative sum. This assumes that we do not reinvest our profits. Our simple strategy has two parameters, the two lookback windows, and in the next section, we will build a system that tests a wide array of parameters to figure out the best ones. There are a number of different ways to generate parameters for our strategy. The most obvious is to select a range, and then try every possible parameter within that range. Since our lookback windows are integers, we could step through lookbacks from 2 to 200 and gather the results. However, this would mean we need to run close to 20,000 backtests, which might take a long time. Furthermore, if we terminate our parameter sweep early, we would only have covered a small square in the full parameter space. Often, a better approach is to choose random parameters. This quickly maps the parameter space more evenly, and when we terminate early, we have a good coverage, just with lower density. This figure shows how we map the parameter space of 100 values with a fixed grid in blue and random values in red. The code shows the procedure, where R is an n by 2 array of n parameter pairs. We have two loops, one that loops through the parameter pairs and another that loops through the stocks. Finally, we calculate the daily return of our portfolio as the mean of all the returns. This means that our portfolio is equally weighted. It is of course possible to have weighting schemes that may be better suited to the strategy. Finally, we calculate the Sharpe ratio S of the strategy as the ratio between the mean and the standard deviation of returns. The value of 16 is the square root of the approximate number of trading days in a year, which is typically between 252 and 256. After wrapping this code in a function called sweep, we can run the function. First, we create an array of 500 random lookback pairs with values between 2 and 199. These are then plugged into the sweep function, and we are ready to go. Python also has a number of optimizers we could use. For example, the scipy.minimize package. And there are also packages for simulated annealing and genetic algorithms. However, there are various reasons why you would build your own sweep. First of all, most optimizers do not deal well with optimizing for integer values, as it is the case here. Second, the response function of our backtest is discontinuous and full of spikes, so any gradient-based optimizer would struggle at best. Finally, it is often quicker and easier to build your own. It may not be as efficient in some ways, but you have full control over its functionality. Furthermore, as we see later, finding the best strategy usually does need some discretion and manual work. While it is great to find the perfect parameters, we know too well that all this does is lead to overfitting, and past results are by no means an indication of future performance. How can we be more confident that our strategy actually delivers? The first question to ask is, regardless of the performance of individual parameter sets, will our strategy's historical P&L correlate with future performance? We don't necessarily expect a perfect correlation, but at least some indication of consistency. The way to do this is to split our results into an in-sample and out-of-sample set. But rather than finding the best in-sample set and test if it also works on the out-of-sample data, we correlate all in-sample results with all out-of-sample results, regardless of their performance. This way, we don't throw away any useful information and get a much better overall indication if the strategy has any merit. This figure shows the correlations for our in-sample and out-of-sample Sharpe ratios. The period is 20 years with an in-sample length of 3000 days. We can see that there clearly is some correlation. We don't expect this to be a perfectly straight line with an R squared of 0.99. Seeing that the strategy has a tendency to permutate past performance into the future with some confidence is as good a result as we can expect for the most part. However, one problem is that depending on how we choose a particular cutoff point for our in-sample data length, the results may look widely different. One way to cross-check if this is the case is to loop through a number of different cutoff periods. The figure shows that we get consistent behavior for different periods for Oracle. Of course, we can also do this for multiple companies. To implement this in code, we first build a function to draw our linear regression line. There are multiple ways to do that using scipy, sklearn, or numpy as shown here. First, we fit our in-sample and out-of-sample metrics, in our case the Sharpe ratio. Next, we create a set of evenly spaced x values with linspace, and finally we create the y values plugging in the regression coefficients m. Now we can build our test function. In it, we split our data into in-sample and out-of-sample, and then apply a metric function to both. This metric function could be the calculation of the total profit, daily P&L, or any other metric. In our case, we chose the Sharpe ratio, and we see later how to pass it into the strategy. We then plot the linear regression line and the data points as seen in the previous plots. To run the function, we need to specify our metric, which we do here in the form of a lambda function. Well done! We have run a parameter sweep on a moving average crossing strategy and found that for Oracle, the in-sample results correlate with the out-of-sample results, and this is true for a range of cutoff points. Now that we know that our strategy has some merit, let's see if we can extract the best parameter sets and build a stable strategy from it. Remember that you can find the Jupyter notebook for this course in the link below. In the next video, we will dive deeper into the subject and extract the best parameter sets from our observations in order to create a stable, profitable strategy. Don't forget to subscribe and see you in the next video.